Chemistry. This is the second lesson of the Foundations unit. It deals with units of measurement and with another concept that's important in science, which is precision and accuracy. So units of measure are essential in chemistry and in other sciences. Units of measure are the word or abbreviation that comes after a number to indicate what you're dealing with, what that number represents. So if I say to you, do you want 10? You would respond 10 what? 10 pizzas, 10 books, 10 what? So in this example, books and pizzas are the unit of measure. They indicate to what the number is referring. All right, so these are the common base units of measure. The one that you're going to hear almost every day is grams, and that's the amount of matter in an object, basically how much it weighs. There's a technical difference between weight and mass that you learn in physics, but in chemistry we really treat the two words interchangeably. So weight and mass mean the same thing. So technically grams is a measure of mass. Liters is a measure of volume. You've all bought a 1 liter or 2 liter bottle of water or soda, and that's the amount of space that it takes up. A meter is the base measure of length. It's how long something is. Now, if you take square meters, you have a unit of area, like how much area the classroom is, or cubic meters would be an area of volume. You could figure out how many total cubic meters are in the classroom, not only the floor area, but from the floor up to the ceiling of the room. Now, time is standard seconds, minutes, hours, what we're all familiar with. Temperature is measured in Kelvin or centigrade. We'll get into that concept later on. We don't use the Fahrenheit scale, which is used commonly in the United States. We don't use that in science or chemistry. And finally, energy is measured in a unit called a joule. And that can be any type of energy. It can be heat energy, sound energy, light energy, energy that goes into throwing a ball, which is mechanical energy. All of those have a common unit of measure, and that's called a joule. So these prefixes, those are words that come before, can be placed in front of a unit of measure to assign a number value. So the most common ones we will use, let's just go down them one by one. Tera is 1 trillion. Giga is a billion. Mega is a million. Kilo is 1,000. We don't ever use hecto or deca. They just aren't used conventionally in chemistry. Deci is rarely used. Now we're getting to units that are less than 1. Centa is commonly used in chemistry, like centigrams or centimeters. Milli is 1/1000th. Micro is 1/1,000,000th. A nano is 1/1,000,000,000th, and pico is 1/1,000,000,000,000th. We actually will get into some of those very small units in chemistry. So a prefix symbol such as micro, nano, or kilo in front of the unit of measure indicates a power of 10 to be multiplied by the number in front. So here are some examples. So 6.7 micrograms means 6.7, go back to the previous chart, times 10 to the minus 6th grams. That's in scientific notation, which you now understand, and there's the decimal version. It's 0.000067 grams. 430 nm is 430 nanometers. A nanometer is 10 to the minus 9th from the previous chart, so that would be 430 times 10 to the minus 9th meters. And there you can see the decimal notation on the right. And finally, 230 kilojoules. That would be 230 times 10 to the third. That would be 230,000 joules. Now we're going to deal with the concepts of accuracy and precision. So the accuracy of a measurement indicates how close it is to a known true value. So that assumes you know what the known true value is. Generally in chemistry we do know that in this level of chemistry. So the way you would measure the accuracy, we'll talk about that in a second. So the precision of a measurement indicates how closely grouped measurements are. So let's look at accuracy and precision. And the typical metaphor for that or example is a bullseye. You're throwing darts. Okay, so this is low accuracy. You're trying to hit that red dot in the middle. That's called the bullseye. So if you're trying to hit that, that shows low accuracy because your darts are all over the place, and low precision because they're not grouped tightly together. So the darts are not near the bullseye center dot, and they are not close together. So that's low precision, low accuracy. All right, this example we have low accuracy but high precision. So the darts are not near the bullseye, but they are close together. So that's low accuracy and high precision. So it means maybe your aim is just a little bit off. You're pulling your arm a little bit to the left. But so you're getting them all to be in the same place, but they're not accurate. They're not where you want them to be. So that's high precision, low accuracy. Next, we have high accuracy, low precision. So the darts are pretty close to the bullseye, but not closely grouped together. So you're getting close to the bullseye, but they're all around the bullseye as well. So that would be low accuracy. So high precision, low accuracy. And finally, we have high accuracy, high precision. The darts are near the bullseye or in the bullseye, and they're all grouped closely together. So that's high accuracy, high precision. So accuracy is measured by percent error. Percent error is the percent difference between the true value, the known value, and the value that you measured in the lab. And there's the formula. So the percent error equals the true value that we know from, say, a book, for example, minus what you measured in the lab, divided by the true value, and then you multiply that by 100%. So example, a student measures the heat release from a reaction as Q. Q is the abbreviation for heat. We'll get into that later. 15.7 kilojoules. The known value for the reaction from experiments and from books where it's been measured accurately, the known value is 16.5 kilojoules. So that's the true value. So you take the true value minus your value divided by the true value, multiply by 100%, and you get 4.8. Those two vertical lines are absolute value symbols. That means the number is always going to be a positive number. If your measured value was greater than the known value, you would have ended up with a negative number there. So the absolute value turns it into a positive number. So you always get a positive number for this particular measurement. The absolute value brackets mean the answer will always be a positive number. Precision is how closely grouped the measurements are to one another. So precision is determined by something called the standard deviation, and that's the Greek letter sigma. It looks like a sideways lowercase a or whatever you want to make that out to be. So that's sigma, and it's abbreviated SD, standard deviation. Standard deviation gives a number value for how spread out your measurements are. So there's the formula. It's kind of not a real pretty looking formula. So let's just work one or two examples with this formula. And we'll define what all of that means. So let's say we have two sets of numbers. Set 1 is 19, 20, and 21. Set 2 is 10, 20, and 30. Now, if you take the averages of those two sets, you do it by adding them up and then dividing by how many numbers you have in the set. So for the first set, it would be 19 plus 20 plus 21 divided by 3 would give you 20. For set 2, it would be 10 plus 20 plus 30 divided by 3. That would also give you 20. So both of these sets of numbers have the same average. So both sets have the same average 20. However, the values of set 2 are more spread out. You can see that pretty clearly. So how do we measure that degree to which they're spread out? So here's a data table. So first, you list the data values. So there's 19, 20, 21. We're taking set 1 first. Then you take the average, which is called the mean in statistics, right there, and you put that in all three rows right there. Then you take the difference, you subtract. So 19 minus 20 is negative 1, 20 minus 20 is 0, 21 minus 20 is 1. Finally, you square that difference. So negative 1 squared is 1, 0 squared is 0, 1 squared is 1, and then you add those up. 1 plus 0 plus 1. That's the capital letter sigma. Has nothing to do with the lowercase, except we happen to be using it in the same problem, and that's the summation sign that you might remember from math. So you sum up those differences squared, and you get 2. Over in the lower left corner, you notice we have n equals 3. So that's how many numbers we have. We have 3 values. So now we're going to take this information and plug it into that formula. So there's the formula. So let's look at what it means. The standard deviation, which is the lowercase sigma, equals the square root of the sum of the deviations squared. That's that 2 number you see on the very bottom right. Over n, that's the number of values, 3 minus 1. And then you take the square root of all of that. Don't try to understand why this equation works. That's not at all important. Just know how to plug in the numbers and how to find a standard deviation. Generally, you do this on a spreadsheet, or your calculator can do it also. So now we're going to find the standard deviation of set 2. So again, we list the values 10, 20, 30. The mean was the same for the set 2 values. You take the difference, 10 minus 20 is negative 10, 20 minus 20, and 30 minus 20 is 10. You square those differences to get 100, 0, and 100, and you add up those differences to get the big sigma, that's 200. You still have n equals 3 as the number of values. There again is the formula. So now we're going to plug both of these data in and see what the standard deviation is of each of these sets. So there are the 2 sets again. So for the first one, we got the capital sigma. The sum of the sigma squares, the differences squared, was 2. The number of numbers was 3, and then you subtract 1 from that. That's part of the formula. And take the square root, you'll get 1. For the data set on the left, we got the sum of the difference squareds was 200. Again, you have 3 values minus 1. And you take the square root of that and you get 10. So you can see that even though they have the same average, 20, the set on the right, which is clearly the set 2, which is clearly more spread out than set 1, has a higher standard deviation. Again, you don't have to understand exactly what that means right now. Just understand the higher the standard deviation, the more spread out the data. The lower the standard deviation, the more tightly grouped together that the data is. So the higher standard deviation of set 2 indicates that the data in this set are more spread out than the data in set 1. So this is a fact of what's called a normal distribution or a bell curve. We'll show you one of those in a moment. So 68% of the values will fall within one standard deviation, either to the right or to the left of the mean. This data set is not enough data points to see that here, but we will see an example that will show that a little more clearly. Okay, so this is called a normal distribution. It's sometimes known as a bell curve. It's the basic kind of distribution that you have in statistics. So in the middle, where the curve is the highest, that's the mean, that's the average. They designate that by the Greek letter mu, mu, lowercase mu. And if you go into the pink region, to the right and to the left of mu, you have 34.13 to the right, 34.13 to the left. If you add those two numbers together, you get roughly, rounding it, 68%. So that's the 68%. That's plus or minus one standard deviation from the average. So 68%, roughly 2/3 of your values, will fall within that pink region. If you go 2 standard deviations, that's the light blue, then you're going to 13.59 to the right, 13.59 to the left. If you add all of those numbers, the blue numbers and the pink numbers, you get about 95%. So that means virtually every value is going to be within 2 standard deviations of the mean. And finally, the light green is 3 standard deviations, and you almost get 100%, not quite, about 99.7% that are going to be either in the red, the blue, or the green, either to the right or the left. So that's true of a normal distribution. If it's not a normal distribution, that would not apply. But in basic statistics and analysis, we assume that most things will fall near the median, the average, and then as you get further from the average, there will be fewer of those in number. That's what probability density means on the vertical axis of that graph. So why does standard deviate? What does it really mean? A normal distribution, also known as a bell curve, has values evenly distributed around the mean, the average. So on a normal distribution, about 68% of the values will fall within 1 standard deviation of the mean in either direction. The pink area on the distribution to the right represents plus or minus 1 standard deviation, plus being to the right, minus being to the left. 1 standard deviation from the mean. Okay, so the following shows scores. This is an example problem of on a 12-question quiz. If you count up, you have 22 students that took the quiz. There's 22 different numbers there. So if you take the mean of this, I just went ahead and did that. It's 7.6. It's somewhere between 7 and 8. It's 7.6. And the standard deviation, computed the way we did on the previous slides, is 2.1. So if you take 7.6 plus 2.1, that gets you up to about 9.7. And if you take 7.6 minus 2.1, that's minus 1 standard deviation, that gets you down to around 5.5. So that means 68% of the value should be between 5.5 and 9.7. So this means about 68% of the value should fall between 7.6 plus 2.1, which is 9.7, and 7.6 minus 2.1, which is 5.5. So we actually see 14 of the 22 values are there. That's 64% of the values fall within plus or minus 1 standard deviation of the mean. The discrepancy, the reason we didn't get exactly 68%, the discrepancy is due to the fact that the data does not form a perfect normal distribution. It's also a small amount of data. If you get closer to 100 data points instead of 22 that we have here, test scores, then you'll get closer to that 68%. All right, and that takes care of this lesson on units of measure, as well as precision and accuracy. We will use this in all of science, and we'll be using this later in the class. So that takes care of this lesson.